Good day, everyone. We are from the Department of Statistics of the CUHK. Today, we will be diving into an interesting topic, logarithmic differentiation. This method offers a unique approach to differentiating complicated functions that can be difficult to solve using traditional methods. So, let's get started. To begin with, let's take a closer look at the idea behind logarithmic differentiation. This method involves taking the logarithm of a function and then differentiating it. We use this approach when it is easier to differentiate a logarithm of a function than to differentiate the function itself. This approach allows us to calculate derivatives of power, rational and some irrational functions in an efficient manner. Now, let's move on to the first theorem, which is displayed on the screen. This theorem states that if y equals f of x, then y prime equals f of x times the derivative of the natural logarithm of f of x. To prove this theorem, we take the natural logarithm of both sides, differentiate both sides, use the chain rule as y is a function of x, and finally solve for y prime. Now that we have a good understanding of the theorem, let's take a look at how we can apply it. Here we have a guideline for logarithmic differentiation. Given a function y equals f of x, the following steps outline the logarithmic differentiation process. First, take the natural logarithm of both sides of y equals f of x to get natural logarithm of y equals natural logarithm of f of x and simplify using logarithm properties. Second, differentiate implicitly with respect to x and solve for dy over dx. Third, replace y with its function of x, that is f of x. Let's take a look at an example on the next slide. We are asked to differentiate y equals x raised to the power of x. Using logarithmic differentiation, we take the natural log of both sides to get natural log y equals x times natural log x. Then we differentiate implicitly to get y prime over y equals natural log x plus 1. Solving for y prime, we get y prime equals y times 1 plus natural log x, which is equal to x to the power of x times 1 plus natural log x. On the next slide, we have the same example where we are asked to differentiate y equals x raised to the power of x. We are using another method, namely the exponential and logarithmic function. The solution is shown on screen. The main idea is to apply that fact that x equals to e to the power of natural log of x and to apply the chain rule. Moving on, let's talk about derivatives of power exponential functions. Logarithmic differentiation method allows us to effectively compute derivatives of power exponential functions, that is functions of the form y equals u of x raised to the power v of x, where u of x and v of x are differentiable functions of x. Let's take a look at an example on screen where we are asked to differentiate y equals the xth root of x over x greater than 0. Using logarithmic differentiation, we take the natural log of both sides to get natural log y equals 1 over x times natural log x. Then we differentiate implicitly with respect to x and solve for y prime to get y prime equals 1 over x squared times 1 minus natural log x. Next, everything is multiplied by xth root of x, which simplifies to y prime equals 1 minus natural log x, all multiplied by x to the power of 1 over x minus 2. On the next slide, we have another example where we are asked to differentiate y equals e raised to the power x. To solve this, we have to take the natural logarithm of both sides to get natural logarithm of y equals e to the power of x times natural logarithm of e to the power of x equals e to the power of x times x. Differentiate both sides implicitly with respect to x to get the derivative of natural logarithm of y equals the derivative of e to the power of x times x. Apply the product rule to get 1 divided by y times y prime equals the derivative of e to the power of x times x plus e to the power of x times x prime. Simplify to get y prime divided by y equals e to the power of x times x plus e to the power of x. Multiply both sides by y to get y prime equals y times e to the power of x times x plus 1. Substitute y with e to the power of x raised to the power of e to the power of x to get y prime equals e to the power of x raised to the power of e to the power of x times e to the power of x times x plus 1. Simplify to get y prime equals e to the power of x raised to the power of e to the power of x plus 1 times x plus 1. On the next slide, we have another example where we are asked to differentiate y equals 1 minus 3x raised to the power cosine of x. This looks much more complicated than the previous examples but is in fact only slightly more complicated. The process is pretty much identical, so we follow the guidelines again. We will take the natural logarithm of both sides to get natural logarithm of y equals natural logarithm of 1 minus 3x raised to the power of cosine of x. This equals cosine of x times natural logarithm of 1 minus 3x. Differentiate both sides implicitly with respect to x to get y prime divided by y equals negative sine of x times natural logarithm of 1 minus 3x plus cosine of x times negative 3. Divided by 1 minus 3x. Simplify to get y prime divided by y equals negative sine of x times natural logarithm of 1 minus 3x minus cosine of x times 3 divided by 1 minus 3x. Multiply both sides by y to get y prime equals negative y times sine of x times natural logarithm of 1 minus 3x plus cosine of x times 3 divided by 1 minus 3x. Substitute y with 1 minus 3x raised to the power of cosine of x to get y prime equals negative 1 minus 3x raised to the power of cosine of x times sine of x times natural logarithm of 1 minus 3x plus cosine of x times 3 divided by 1 minus 3x. We end this section with a recap on differentiating functions with exponents. On screen you can see 4 rules: constant rule, power rule, derivative of an exponential function, and logarithmic differentiation. It is easy to get these various functions confused and use the wrong rule for differentiation. Always remember that each rule has very specific rules for where the variable and constants must be. For example, the power rule requires that the base be a variable and the exponent be a constant, while the exponential function requires exactly the opposite. As we encounter more complex functions, differentiation using the product and quotient rules can become tedious and error-prone. Logarithmic differentiation allows us to simplify these calculations and arrive at an accurate derivative. Let's take a look at theorem 3.1. This theorem states that if f x equals g x times h x, then the derivative of f x with respect to x is equal to g x times h x times the sum of g prime of x divided by g x plus h prime of x divided by h x. Here's how the proof goes. We take the natural logarithm of both sides, and then differentiate implicitly with respect to x. We arrive at an expression that allows us to calculate the derivative of f x using only the derivatives of g x and h x. The result is the same as after applying the product rule directly to f x. Similarly, theorem 3.2 states that if f x equals g x divided by h x, then the derivative of f x with respect to x is equal to g x divided by h x times the difference between g prime of x divided by g x minus h prime of x divided by h x. To demonstrate this theorem, we again take the natural logarithm of f x and simplify using logarithm properties. We then differentiate implicitly with respect to x to arrive at an expression for the derivative of f x. Note that the result is the same as after applying the quotient rule directly to f x. Let's take a look at an example on screen where we are asked to differentiate y equals x squared times x minus 1 times x squared plus 4 raised to the power 3. The natural logarithm of y equals the natural logarithm of x squared times the quantity x minus 1 times the quantity x squared plus 4 to the power of 3. This equals the natural logarithm of x squared plus the natural logarithm of the quantity x minus 1 plus the natural logarithm of the quantity x squared plus 4 to the power of 3. This equals 2 times the natural logarithm of x plus the natural logarithm of the quantity x minus 1 plus 3 times the natural logarithm of the quantity x squared plus 4. The derivative with respect to x of the natural logarithm of y equals y prime divided by y, which equals 2 divided by x plus 1 divided by the quantity x minus 1 plus 3 times 2x divided by the quantity x squared plus 4. Therefore, y prime equals y times the quantity 2 divided by x plus 1 divided by the quantity x minus 1 plus 3 times 2x divided by the quantity x squared plus 4. This equals x squared times the quantity x minus 1 times the quantity x squared plus 4 to the power of 3, all multiplied by the quantity 2 divided by x plus 1 divided by the quantity x minus 1 plus xx divided by the quantity x squared plus 4. On screen you can see another example where we are asked to differentiate y equals x plus 2 raised to the power 3 times 2x plus 1 raised to the power 9 divided by x raised to the power 8 times 3x plus 1 raised to the power 4, where x is greater than 0. Note that using product and quotient rules is very tedious. Apply logarithmic differentiation instead. The solution uses logarithmic differentiation to make the process easier. The fraction is split into two parts, the numerator and the denominator, and the natural logarithm is taken of both parts. The logarithm of the numerator is simplified by using logarithm properties, and the same is done for the denominator. The derivative of the natural logarithm of the fraction is then found by differentiating implicitly with respect to x. Finally, the derivative of the original fraction is found by multiplying the fraction by the derivative of its natural logarithm. The final result is a fraction with a complicated expression in its numerator and denominator. On screen you can see another example where we are asked to differentiate y equals cube root of x squared minus 3 divided by 1 plus x raised to the power 5, where x is greater than square root of 3. This is a problem that involves finding the derivative of a non-rational function. The solution uses logarithmic differentiation to make the process easier. The natural logarithm is taken of the function and simplified using logarithm properties. The derivative of the natural logarithm of the function is then found by differentiating implicitly with respect to x. Finally, the derivative of the original function is found by multiplying the function by the derivative of its natural logarithm. The final result is a complicated expression involving fractions and radicals. We end this presentation with an application of logarithmic differentiation, maximum likelihood estimation. On screen you can see an example where we define the likelihood function L as a function of parameter theta and observed values x1, x2, x3, xn. The goal is to find the value of theta such that L attains its maximum. The solution uses the basic property that e to the power of a times e to the power of b equals e to the power of a plus b. The natural logarithm is then taken of the likelihood function and simplified using logarithm properties. The interim result is an expression involving n times the natural logarithm of theta minus theta times the sum of xi values from 1 to n. The second part of the solution involves differentiating the natural logarithm of the likelihood function L with respect to theta and setting the derivative equal to 0. Solving for theta, the maximum likelihood estimator of theta is found to be n divided by the sum of xi values from 1 to n. In brief, maximum likelihood estimation (MLE) is a method of estimating the parameters of an assumed probability distribution, given some observed data. This is achieved by maximizing the likelihood function so that, under the assumed statistical model, the observed data is most probable. In this example, we found the maximum likelihood estimator of theta for a random sample x from an exponential distribution with parameter theta. In statistics, it is represented by theta hat subscript ml. To summarize, we have covered the concept of logarithmic differentiation and its applications, including how it can be used to differentiate complicated products and quotients. We also looked at various examples of how to use logarithmic differentiation to find derivatives of different functions, including power exponential functions. Remember to always pay close attention to the variables and constants in the function and use the correct rule for differentiation. Thank you for your attention, and I hope you found this presentation informative and engaging.